right, so Tim Roughgarden will tell us about how hard is inference for structured prediction.
Okay. Thanks, everyone. So this is joint work with Amir Globerson from Tel Aviv and David Sontag and Schaefer Yildirim from NYU. And don't let the title fool you. Okay, so it's true that we were motivated by applications in machine learning. It's true that it appeared in ICML, a machine learning conference. But the secret is that actually most of this work is really theoretical results about what I think is a very appealing combinatorial model, which actually has a lot of open questions that I think many people in this room are really well suited to make progress on. So I'll try to highlight those opportunities as we go through the talk. All right, but let me just at least say one slide. What were we motivated by on the machine learning side, and what the heck is structured prediction anyways? So in structured prediction, we're given a bunch of objects, and we have information about the relationships between these objects. We want to use that information to predict labels for all of the objects at one time, in one batch. And we want to be smarter, we want to be more intelligent than just independently predicting each of the objects without any of the relationship information between them. So one canonical application, and the one that really motivated us, was from computer vision, specifically image segmentation. So here the objects would correspond to pixels. The relationship information, that could be information about adjacent pairs of pixels. And what you're trying to predict is, for example, a segmentation into a foreground and a background. So for each object, you're giving it a binary label. Is it in the foreground? Is it in the background? And I'll bet it's easy to imagine that using information about adjacent pairs of pixels allows you to do much better than just predicting looking at each pixel separately. Okay? Lots of other applications, like in natural language processing. Sometimes you have a sentence, you want to infer, what is the role of each word in the sentence, and you can imagine you might want to use information, for example, about consecutive words above and beyond just predicting each word separately. Okay. And then I guess one final comment, on this slide, just to clear up any confusion. So in theoretical computer science, there's been a lot of really nice work lately on the interface with machine learning. A lot of the works that you may have seen have really been about the complexity of learning a model. So maybe in a supervised setting, given labeled training data, or in an unsupervised setting, given unlabeled data, try to compute a model which seems to fit the data. And that's not what we're doing. Okay? We're assuming that we already have learned the model. Okay, so we're going to be assuming a generative model on the input. We'll just take it at face value, and the problem will just be inference. Given this model that we believe, what actually are the labels of these objects? And of course, if you're trying to predict, a bunch of pixels at once, a binary labeling for each, even the inference problem, right, has an exponential number of outputs and can be quite interesting. Okay. All right, so let me jump into the model. Actually, not really the model. This is sort of a silly version of the model, but let's start here anyways. So you're given a graph, and you know this graph. So this could be, for example, a grid in the image segmentation situation, where each edge denotes an adjacent pair of pixels. There's a ground truth binary labeling. So this would be, for example, the real segmentation of the image into the foreground and the background. So that's going to be X, labels each node 0, 1. That's what these red and blue colors denote. This you do not know. Okay? This is what you want to compute. Okay? So if you don't know X, if you don't know the labeling, what do you know? Well, suppose I gave you, this pairwise relationship information. Okay, so for each edge of the graph, suppose I told you whether the two endpoints belonged to had the same label, or whether they had different labels. Okay, so a plus here means that the labels of the endpoints are the same. Minus means that they should be different. The goal then is, given this information on the edges, recover this secret binary labeling of the vertices. So does this seem like a hard problem? May not be unique, but it's unique up to a relabeling of the two colors. Yeah. So this is not a hard problem. Okay. So if the graph is connected, just color some vertex arbitrarily, like maybe you color that one green, and now you just propagate across the edges, right? Given that that's green, these are red. Given that all of these are pluses, you then know all of these are red, and so on. If you guessed wrong, then you get the ground truth except with the order of the colors reversed, and that's perfectly fine for our purposes.
So you're assuming no errors in the data?
I said this was the silly model. Yeah. So the silly model, there's no errors, and it's an easy problem. Okay? But hopefully everyone's clear, at least so far. All right. So the interesting problem is when you want robust recovery results, so where I don't actually give you the parity of every edge, but rather I give you noisy parities. Okay? So the model is going to be that on each edge independently, with probability p, you get the flipped version of the actual parity. Okay, so I think compared to the previous slide, I flipped these two. These were minuses, now they're pluses. And these used to be pluses, and now they're minuses. Okay, so those are the 4 misleading edge labels. Okay. So given noisy edge parities, the goal remains the same. You want to recover this binary labeling of the vertices, or if you can't do it exactly, you'd like to get as much of the unknown labeling correct as possible, as many of those vertices correct as possible. Okay? So that's the model. Okay. So what do we want? So the objective we're going to look at is we're going to look at minimizing the worst case expected error. By error, I just mean the Hamming error between the output of an algorithm and the unknown ground truth. Okay, so just the number of vertices that are misclassified by the algorithm. So the algorithm is just a mapping, right? So the graph, think of the graph as fixed. It takes as inputs the plus minus labelings on the edge, and it outputs a binary labeling. We're going to take the worst case over the unknown ground truth x. D of x here denotes the distribution on inputs on plus minus labels, given that the ground truth is x. L is a given set of edge labels. This is the output of our algorithm on those edge labels, and this is the error with respect to the ground truth. Okay, so like a lot of the work in sort of beyond worst case analysis, this has sort of a hybrid flavor. It sort of is in between worst case and average case analysis. Worst case over the ground truth, but then average case over the distribution on inputs given the ground truth. Okay, so that's what we're going to be after. Any questions about that?
May output randomized.
Say it again?
The output of the algorithm could be of distribution.
It could. I mean, we're not going to have a reason to do that, but it could. Yeah.
So this seems quite related to correlation.
It is. Yep, we'll get to that. It is. The one thing I want to point out right now is that in correlation clustering, the objective function is with respect to the edges. So there is not, or at least in the version of the problem often studied in like approximation algorithms, there's no ground truth, there's only data, and you just want to get as many edges correct as possible. Here, we don't care about how many edges we get correct, except in as much as it leads us to a labeling of the vertices which is accurate with respect to the ground truth. So it's kind of a difference of viewpoint compared to the usual approximation algorithms viewpoint.
Oh, well, you can cast correlation clustering as a structural prediction with triangle, right, constraints. Instead of pairwise, you have triangle for sets of three edges. If you
Sure, but again, so the way correlation clustering is usually done in approximation algorithms is different, is with a different objective. I just wanted to make that point. In the theoretical computer science world, okay? And so, but as we'll see, the algorithm will be correlation clustering. So there is a very strong connection, okay? Other questions? Yeah, Roby.
So yes, the graph and the hidden labeling are worst case?
The graph I'm thinking of is fixed. So we're going to be interested in results that vary with the graph G. Okay, so there will be some bad graphs, there will be some good graphs, and the whole point of the theorems will be to understand which are which. Okay, so think of the graph G as fixed but arbitrary, and then what the graph is will shape the results in interesting ways.
Okay.
All right, so that's fine. So this is our goal. You know, we want an algorithm with minimum expected error, but I mean, what are the theorems going to look like? Right? So for a fixed graph, there's only a finite number of these algorithms, and one of them is best. You know, so what? Okay, so what do we want to prove? Well, two things. So first of all, you know, even ignoring computational efficiency issues, just information theoretically, what is the minimum possible expected error that is achieved by any algorithm? Not necessarily efficient. Is it 0? If it's not 0, what is it? How does it depend on the parameters of the problem, of the model? Okay, what are the parameters of the model? The graph G and this noise rate P. Okay, so both of those might play into what is the minimum expected error possible. We want to understand that. Now, of course, computational efficiency is also interesting. So ideally, in a perfect world, you'd like a polynomial time algorithm which gets worst case expected error as small as the information theoretic lower bound. Okay, that would be sort of the holy grail here. Okay, and hopefully that error is pretty close to 0, is small. All right.
Okay.
So how? So you still will probably have this sort of up to flipping.
That's right.
So do you have some sort of like list decoding or?
Yeah, that's one way to think about it. I mean, the paper has a more general model where you also get some signals from the nodes, and then you can use signals from the nodes to tie break between all the elements in your list. But for this talk, think of it as list decoding. There's always going to be really two outputs, you know, one and then the sort of flipped version of it, and then some downstream user can figure out which one is actually the foreground, which one's actually the background. Yeah. Yeah.
But in terms of your statement about the expectation, that means that you're going to have at least like a 50% error as just a lower bound from that.
Sure. So, okay. So what I really mean is the error of the better of the labelings output by the algorithm and the flip of it. Okay. So I want to be totally precise. That's what this should say. Yeah. Other questions? Okay. So I realize this is a new model for many of you. So let me build your sort of understanding of this model and how it might work by an analogy to a pretty closely related model that I think many of you have seen at some point, namely the stochastic block model. So there's been a ton of work on the stochastic block model over the past few years. Sometimes this is called the planted partition model, or it's called the community detection problem. So for example, Aravindan on Monday, his talk was about recovery in stochastic block models. So the simplest version of this would just be like a planted bisection problem. Okay, so you could imagine that there's n over 2 people or n over 2 vertices that belong to one community A. The other n over 2 vertices belong to some other community B. You don't know what that partition is. You want to figure it out. And what information are you given? Well, you're given random edges. And the trick is that the density of the random edges is going to be higher inside the communities A and B than across A and B. Okay, so this will be relatively sparse compared to the edge density in here and in here. And then it's plausible you could reconstruct who's in A and who's in B given those edges. Okay? So that's recovering the stochastic block model. And this bears a lot of resemblance to the structured prediction problem. Okay, so the biggest difference is there isn't really an arbitrary graph G in stochastic block model. There is this set of vertices, okay? But remember, in the structured prediction problem, there's a graph G like the grid, and you only get pairwise information about the endpoint, about 2 vertices that are the endpoints of an edge. Okay? In the stochastic block model, every single pair of vertices you may or may not have an edge. So you get a noisy signal about every pair of vertices in the stochastic block model. So if you like, think of that graph G as being the complete graph in the stochastic block model, not something like a grid. Okay? So that's the first biggest difference, but otherwise, what else? We have an unknown binary labeling, okay, who's in A and who's in B. We get a noisy version of edges, and we want to do recovery, okay? The other way in which it's different, which I want to emphasize less, is just that the noise is asymmetric in the stochastic block model, whereas it's symmetric in the structured prediction. So recall in the model I presented, for every parity, it doesn't matter if it's a plus or a minus in the ground truth, it gets flipped with the same probability P. For the stochastic block model, okay, so what would it mean to have like no noise? No noise would mean I give you 2 cliques. One clique on A, another clique on B, no edges in between. But there's noise. A lot of the edges inside A and inside B are going to be missing in the graph you get, and some of the edges between A and B are going to be present. And the usual parameter regime studied in these models, there's a very high error rate inside A and B. Okay, so you don't get a clique, you get something with much fewer number of edges, but then the error rate is very low across the cut. Okay, so with no noise this would be empty, but you don't allow too many edges here in the usual parameter regimes. Okay, so those are the 2 big differences. So the similarities are, you're again given edge information, want to recover this unknown binary labeling, and the objective function is the same. You want to get as many of the vertices right as possible. The big difference is that the structured prediction model includes a graph G, okay, a combinatorial object. So theorems about the stochastic block model, what are they parameterized by? Well, what's available, what are the knobs you have in this model? You have the edge density inside the communities, and you have the edge density between the communities. Maybe you also have like the number of clusters, if you have more than 2 clusters. So all of the theorems are about that, are in terms of these numerical parameters of the edge densities and the number of clusters, whereas in structured prediction, there's this extra parameter, a combinatorial object, the graph. So we're going to have theorems which actually depend in an interesting way on that graph. Okay? That's the biggest difference. Okay. Good. So let me show you that the graph matters. Okay? There's some graphs which are just sort of hopeless. Okay? Specifically, the path graph is going to be hopeless. So take G to be a path graph with n vertices, with n going to infinity, and you want to do recovery. And let's suppose I'm going to be a really nice guy. I'm even going to give you some advice about what the ground truth is. I'm going to promise you it's a bunch of zeros followed by a bunch of ones. The only thing you don't know is the switch point where it goes from zeros to ones. That's what you're trying to figure out, okay? So if there was no noise at all, right, these would be your edge labels. It would be all pluses except for a single minus indicating to you where the switch point is, okay? But what if there's noise? And let's say not that much noise, so like well subconstant noise, say log n over n, okay? Now what's the input going to be? Well, you're still probably going to have that correct minus indicating you the true flipping point of the labeling, but you're also going to have log n extra minuses that you know are just corrupted parities. So you're just going to be faced with a path with roughly log n minuses, roughly equally spaced between the two. You know one is the correct one, you don't know which, you have to guess. So linear error is going to be inevitable. Okay, so any algorithm is going to have expected Hamming error at least, say, 0.25 times n in this regime. Okay? So that's a bad graph. Okay? Even as the graph grows large and the noise rate goes to 0, the best possible expected error is lower bounded by a constant times n, independent of the noise rate p.
So why is it important to have log n faults?
As opposed to just constant, just 1 over n? Yeah, you can do that too. This way you can say with high probability you know how many minuses there are, but it's not important.
Because you want an expectation in your...
That's right. So it's not important. Yeah. So I just find it helpful. I feel like with this regime I can almost think of it as a semi-deterministic object, which just for me is helpful. But you don't need it. Not important. Other questions? So that's an example of a bad graph, a path, where you actually cannot recover this unknown ground labeling given these noisy edge parities. What got us kind of excited about the problem is when we started running experiments and we were looking, we started with a grid, and we were curious about the grid, because of the applications, because it's sort of the first graph you think about if you're thinking of computer vision applications. Also, there's some technically interesting aspects of the grid, like it's not a good expander, for example. And so the picture here, so full disclosure, this is a slightly more general model than what I'm describing in this talk. This also has node noise, but forget about that. It's also a slightly different algorithm than the one I'm going to talk about, but qualitatively, the points I'm making remain valid. And so the point here is this has a p-value, okay, so a noise rate of 8%. 8% of the parities are getting corrupted. And so then what do? We take a bunch of samples. Okay, so we fix the ground truth to just be everything is 0. Now we corrupt edges at random. We do that 1,000 times. We run our algorithm each of the 1,000 times. And this was the average number of times we made an error in a given pixel. Okay, or in a given vertex for a 20 by 20 grid. And the only sort of point here is that the error, the average error is tracking the edge noise. You can't really see this because I'm just showing you one data point. But if you continue this experiment with different choices for the edge noise, you see the Hamming error, expected Hamming error, drop, it seems, in proportion with the edge noise. Okay, so here we were, at least empirically, on 20 by 20 graphs, getting the kinds of approximate recovery results we wanted. We weren't getting it completely correct, and you don't expect to, as we'll discuss, but this is much, much better than the path, where you're just stuck by, say, 0.2, by 25% error, no matter how big the graph gets.
So do the corners behave that way because they have fewer neighbors?
Yeah. So intuitively, the corner edges are more likely to be tricked because there's just sort of information passing to them. Truth has kind of fewer disjoint roots going to them than somewhere in the middle. Yeah.
So is there any connection to percolation?
There is, actually. Some of our arguments are inspired by percolation arguments. We really wanted to use some deep percolation theorem black box to prove some cool theorem. Couldn't get it to work. But indeed, what we wind up doing, so the connection would be, when an edge is noisy, that would be like, deleting an edge from the grid in an infinite grid.
It
and
looks like disagreement percolation too.
Yeah, and so you care a lot about connected components, in the open graph and percolation, and that's going to be a lot what our proofs look like here. So we don't have an interesting formal connection. I do think there might be one, and certainly, they're reminiscent of each other. I completely agree. Other questions?
So corners being red is because of the algorithm, or there is something with the degree or the position of the node?
That's a good question. You could imagine actually proving an information theoretic lower bound saying that so this is sort of a more fine-grained measure. So this isn't just sort of average error, this is average error pixel by pixel. And I'm going to show you some lower bounds on the best error possible, but it's not going to be pixel by pixel. It'll just be sort of on average. You could imagine stronger lower bounds that even talk about which parts of the graph you're most likely to get wrong. We haven't done that, but I think that would be interesting. Yeah.
What if you put cyclic boundary conditions on this?
Um,
Uniform?
does it what?
Become uniform, or so that
Turn into a torus.
torus?
No, so bounded genus, this tends to work well too. Yeah, I'll talk a little bit about that.
I think
Yeah.
the question was, if you made it a torus,
Yeah.
do you not get these corners looking very different? Does the overall probability become uniform, essentially?
I see. You'd sort of expect so, but we didn't run the experiment on it. But I would expect so. The algorithms are all kind of very symmetric, so I would think so. Other questions? So as I'll show you, the algorithm will not actually exploit the grid. Okay, so in that sense, you'd expect the results to be uniform. Okay, Good. So we want, in theory, to explain this, right? So it seems the grid is behaving in a much better fashion than the path. And then what do the graphs do well? How do we prove we're doing well in the grid, and so on? So this suggests we need a definition to distinguish between bad graphs like the path and potentially good graphs like the grid. Okay? So this, I think, is the definition probably any of you would have written down also. So just qualitatively, getting at what are the good graphs, what are the bad graphs. So we're going to say that approximate recovery is possible in a family of graphs if there exists some algorithm, not necessarily efficient, so that the expected error goes to 0 with the noise rates. Okay, so f of p here is the fraction of vertices you get wrong, and you want that going to 0 as p goes to 0. So to be precise, what are the quantifiers? The quantifiers are for every p greater than 0, there exists an n naught. So that for all graphs in the family with more than n naught vertices, the expected error of your algorithm is at most f of p times n. And that's exactly what we did not have in the path. You can take the noise probability p as low as you want. I can find a big enough graph, like with 1 over p squared vertices, so that your expected error is at least 0.25 times n. Okay? So this is failed by the path. Hopefully it's met by other graphs. Now, so this is just qualitatively. So this is kind of a binary thing. You either satisfy this or you don't. Of course, when you do satisfy this, you want to get greedy. Okay? So maybe you want to not just have an algorithm, but a polynomial time algorithm. And maybe you also want to pin down exactly what is the best possible error rate as a function of p. You'd like the smallest function of p possible. Okay? So those are the kinds of statements we're interested in making. Okay. Any questions at this point? So the theorems in this talk are about exactly sort of this question, these two questions. Was it clear?
When you say which graphs, it shouldn't be a binary. It could be like a parameter of the graph that affects your success, like expansion or...
Yep, and that's exactly where we're going, exactly. But so for a given family of graphs, infinite family of graphs, it's either going to have this property or isn't. Now, we want our theorems to more illuminate what is the structure which drives when this is true. And so that's the theorems we aspire toward, yeah. We don't want a graph family which sort of accidentally satisfies this condition in some sense. Other questions? Okay. So let me tell you about the algorithm. All the results are about exactly the same algorithm, and this is where the connection to correlation clustering comes in. So our algorithm is simply going to be compute the binary labeling of the vertices that minimizes the disagreement with the input. Right, so the input gives you a suggestion for each edge, whether the endpoint should be different or the same, and you want to take as much of that advice as possible. So you incur an error, so the algorithm thinks of its objective function as it incurs an error whenever it assigns two endpoints of a plus edge different colors or the two endpoints of a minus edge the same color. And so it wants to minimize the number of errors of this type over all possible binary labelings. Okay? So this is exactly the correlation clustering problem restricted to two clusters. Or if you're coming from a machine learning background, this is just a suitable maximum likelihood estimator, okay, for the sort of background generative model. Okay. You could have a couple complaints about this algorithm. So one complaint would be about computational efficiency, and indeed it's NP hard to solve correlation clustering in general. The good news is there are some interesting cases where you can actually solve this problem exactly in polynomial time. In particular, planar graphs and bounded genus graphs, using matching techniques, you actually can solve this exactly. So that's nice. Beyond that, it is NP hard. Sampath?
So you're shifting from caring about the vertex errors to edge errors because the vertices are bounded degree, I guess, in this case, right?
Bounded degree is not going to be that important. I mean, it's just a heuristic. So we're using the edges just because it's what we've got. And so all of the analysis work is showing that if you do good on the edges, you do good on the vertices. But as we saw in the path, in general, that's not true. But the hope will be for other graphs, doing well on the edges implies that you do well on the vertices. But that's
if the vertex has a very high degree, then you might be overcounting the error you have around the neighborhood of that vertex, whereas it's only one. It's contributing one to the error. That's why.
That's true. On the other hand, if you have high degree, it somehow has a lot of information in the immediate neighborhood about what it is. If you just take the majority, you start doing well with high degree vertices. So I take your point, but it's not clear it's an obstacle to this heuristic. Yeah. Okay, so polynomial time in planar graphs, not in general. The other thing you might complain about is, it's sort of solving the wrong objective. And this is kind of what Sampath was getting at. Right, so this is a maximum likelihood estimator. So it's maximizing probability of the ground truth given the data. But actually, that wasn't our objective function. Our objective function was to minimize the expected Hamming error. okay? Which is different. It's different than maximizing the likelihood. So in particular, if you wanted to be information theoretic optimal, it would be an algorithm called marginal inference, where you actually sort of compute the posterior over what the ground truth might be given what you've seen, given the data, and then you do each pixel independently with respect to that posterior. So that would be optimal. This, in some sense, is an even heavier machinery algorithm. So while correlation clustering has the flavor of an NP-hard problem, marginal inference has the flavor of a sharp p-hard problem. Okay, so this is, in some sense, an easier, this is a heuristic that's a stand-in for marginal inference. So the issue being, of course, you're not going to get information theoretic optimal in general for this algorithm, but as we'll see, in interesting cases, you do get to within an information theoretic lower bound up to a constant factor. Okay, so it seems like you don't lose much from this heuristic compared to the information theoretic optimal solution. Okay. So this will always be the algorithm. Okay, we'll look at 3 cases. This is always the algorithm. Just minimize disagreement with the input.
When you say a constant factor, do you mean a constant factor of the error estimation or a constant factor of errors in the labeling?
So I mean the expected Hamming error will be at most a constant times the minimum possible for any algorithm, where the constant is independent of p and of n.
And you're talking about the node labels, not the
That's
edge.
right. Yeah, I mean the edges were just getting optimal with respect to the data. Yeah. So that's right. So the objective function is really about classification error. It's about the vertices. Our algorithm is using the edges, but the objective is about the vertices.
Yeah, but you could just as well say, oh, your objective is to recover the edges, but then, because from then you will be able to get the vertices, right?
Well, if the edges were consistent with each other, right. So that's sort of consistent. Sort of reverse engineering a set of edge labels which are mutually consistent is basically the same as computing a vertex labeling.
So that's another difference from correlation clustering.
Which is?
Your objective function.
Absolutely. That's really the main one. We care about the vertices, we don't care about the edges. Yeah. So the algorithm is correlation clustering, but the way we evaluate the quality of the algorithm is different. Yeah. Okay. All right, so let me tell you a little bit about our results and how we prove them. So let me just give you a really simple lemma, but we use it in all of our positive results. We call it the flipping lemma. The flipping lemma is about bad sets. So what's a bad set? Okay, so imagine you have your ground truth. Your algorithm outputs some labeling. Okay, it's got some of the vertices correct. It got some of them incorrect. Imagine you just deleted all of the vertices that were correct from the graph, leaving, shattering the graph into these connected components of vertices you got entirely wrong. Okay, those connected components are the bad sets. Okay, so put differently, it's a maximal connected subgraph of entirely mislabeled vertices. Okay, everything in here is wrong with respect to the ground truth. That's a bad set. Okay, so what is the flipping? So these concern us, right? If you have a big bad set, it means you have lots of Hamming error. So we want to say these are unlikely to occur. Okay. So if a set's bad, what can we say about it? Who's the culprit? Well, it's got to be some corrupted edges, right? That must be why our algorithm screwed up the labeling on S. And indeed, whenever you have a bad set, it must be the case that at least half of the boundary were corrupted. Okay? So you flip that probability P on at least half of the boundary edges. Why is that true? Well, 2 simple reasons. So first of all, and this is where we use the fact we're really optimizing the correlation clustering objective, why did our algorithm label S the way it did? Okay? Well, our algorithm certainly thinks, with respect to the data, it's getting at least half of these edges correct. Why? If it was getting less than 50% of the edges correct, you could just toggle the label of everybody in S. That changes nothing about edges in here or edges in here, but if you toggle everybody's label in S, it toggles the status of every edge between the two. So if previously more than half of these you were getting wrong, now half of them you're going to be getting right with the input. So the algorithm for any set S, by virtue of being optimal, thinks it's getting at least half of the boundary edges labeled correctly. On the other hand, this is a maximal subset of incorrectly labeled nodes. These are all wrong. All of these neighbors are correctly labeled with respect to the ground truth. So with respect to the ground truth, the algorithm's literally getting every single one of these edges incorrect. Okay, every single one of these edges has the opposite parity in our algorithm's labeling compared to in the ground truth labeling. So the only way these 2 things can be consistent is if at least half of these edges were corrupted. Okay? That's the only way these can be reconciled. Okay? So bad sets have half of their boundary being corrupted. All right. So when should I stop, by the way? 10 minutes? Okay. Okay. Let's do this. So a couple warm-ups, okay? So proofs of graphs that you can prove approximate recovery in a single slide, which will lead us to sort of the last result I want to talk about, which is about grids and grid-like graphs. Okay? So just to give you a feel for this problem and how these arguments might go, this is, in some sense, a very easy case, expander graphs, okay? So D-regular, and I'm using the combinatorial definition of expansion. So for every set, most half the vertices, the boundary size should be at least a constant factor of the biggest it could be. The biggest it could be being the degree D times the number of vertices S, okay? So the claim is approximate recovery is possible for any family of D-regular expander graphs. So how would you prove this? Well, think about an algorithm's output. Think about a ground truth and the output of an algorithm. That gives you these bad sets. These, again, are the connected components of things that are incorrectly labeled, okay? The error, right, the error incurred by the algorithm is just the sum of the sizes of the bad sets. Okay, the bad sets are just the mislabeled vertices. Okay, so this is what we want to upper bound. All right? Well, what does the flipping lemma tell us? It says whenever we have a bad set, the only reason that could have happened is because lots of corrupted edges on the boundary, at least half of them. In an expander, we have a lower bound on how many edges there are on the boundary. There's a lot of them. Okay, so if you had 100 vertices that were all mislabeled, it must be that there was C times D times 100 edges, and then half of that on the boundary being corrupted. Okay? So the upshot being is, you can charge the error that you care about on vertices to corrupted edges up to C times D over 2 factor. Okay? So what does that give you? So then summing up over the bad sets, what's the error? Well, you can charge it against the corrupted edges, again, modulo the C times D. One of these factors of 2 is because you only get a half in the flipping lemma. The other factor of 2 is because we're double counting corrupted edges potentially. But in any case, we know the expected number of corrupted edges. Right? That's an easy thing. That's just P times the number of edges. It's a D-regular graph, right? So there's D times N over 2 edges. So that leaves us with an expected error of 2Pn over C, where C, again, is the constant in the expansion condition. Okay? So that's a proof that the algorithm we were talking about, so it shows that expander graphs admit approximate recovery with f of p linear in P. Okay? Questions about that? Okay. So again, so expanders, what's sort of easy about expanders is you can charge vertex errors to edge errors. And so that's what makes that analysis go. So that was simple enough, but believe it or not, there's already a lot of stuff we don't understand even about the expander case. So correlation clustering, expander graphs aren't planar, and correlation clustering is NP hard on expanders. And so we literally do not know of a polynomial time non-trivial recovery result for expanders. Okay? It seems like you should be able to use semi-definite programming or something like that. That's what's driven a lot of the recovery results in, say, the stochastic block model. But we do not have any polynomial time algorithm with a non-trivial error guarantee in this case. Okay. You can also ask about the error rate. Let me skip this. Okay. So you can also hope to do better than P times N. You could hope to get that optimal, which is probably P to the D over 2. Yeah.
Why is the approximate correlation clustering not a give you guarantee?
So I think you'd need a constant factor.
For the minimum objective, there are constant factor approximations.
For the complete graph or for an arbitrary graph? Yeah, almost all of the correlation clustering literature considers only the case of a complete graph, and that's not what we're talking about. So this result by Domain et al., that's the main one that considers general graphs, and they actually establish a rough equivalence to multicut, which suggests that constant factor algorithms might be out of reach. So I guess I should have said that. I mean, to get polynomial time recovery, I think you're unlikely to be able to just take an alpha approximation algorithm, use only the fact that it's an alpha approximation algorithm, and prove something about classification error. But certainly specific algorithms, using what they're doing, like solving a semi-definite program, then I think I would hope that you could have some efficient recovery results. Yeah, good question.
Yeah. But it also seems like the fact that the input is coming from the stochastic model, if you find anything that has, like non-trivial agreement, even from the STP, in terms of how often it agrees with those flips, that seems to be hard to do without actually correlating it somewhat with the clustering, right?
So you're saying you could have a thin end of the wedge and sort of propagate from there?
Yeah, I don't know.
Potentially. I mean, that would be the first way you'd try. I mean, that would be one of the first ways you'd try to do it, in the spirit of old Fagakilian algorithms and that kind of thing. Yeah. Okay. 5 minutes. Okay. So, second case, I'll just mention very briefly. So again, just a family of graphs, which, let me skip this. I don't have time for the grid. let's move on to the grids. All right? So root n by root n grids. Now, like I said, we were motivated by vision applications, so it was natural to focus on the grids, but I understand if it bothers you, if it seems like very specific to just be thinking about grids. So let me tell you actually the two properties of grids that we're going to use for the analysis, and the theorems will be general for lots of these grid-like graphs. So the first thing, we are going to use planarity. In particular, we're going to use that there's a dual graph, and we're also going to use that the dual graph has bounded degree. So in other words, in the planar graph you're given, it should be the case that every face, other than the outer face, should have a bounded number of sides. It's property one we use with the grid. Now, we know we need another property, right, because the path satisfies this. Okay? So what we're going to need is we're going to need a sort of weak expansion property that the grid has. Now, the grid's not an expander, we know that. What would an expander say? It would say, you know, if you have S vertices, the number of edges sticking out is linear in S. So the weak version is just going to say the number of edges sticking out is lower bounded by at least some polynomial function of the size of S. So in a grid, for example, if you have a subset of the grid with S vertices, there's at least square root of the size of S edges on the boundary. Okay? So that's what we use. Notice in a path, this is totally not true. Right? So I can take arbitrarily large subpath, and I only get 2 edges on the boundary. It's not lower bounded by some polynomial function of the number of edges inside. Okay? So these are the two properties we need for our recovery result, but let's just think about grids specifically. So this is where we get the most sort of satisfying result. So it's the same old algorithm, correlation clustering, but as I said, using matching, you can actually solve it in polynomial time for planar graphs like grids. And moreover, the algorithm gets the information theoretically optimal, minimum expected error. Okay? And the optimal rate turns out to be p squared times n. Okay? So the lower bound, if you think about the lower bound, right, it's pretty intuitive. So the grid is 4 regular. So if you have a vertex and exactly 2 out of the 4 edges get corrupted, you basically have to guess what that vertex is. Okay? So for any given vertex, there's sort of a p squared probability. It's going to be ambiguous, and you have no idea. So that's the intuition behind the p squared over n lower bound. Okay? So I'm going to talk a little bit about the upper bound now. All right, so I flashed by this example of graphs that have a large minimum cut. How did that proof go? That proof basically used the fact that in a graph with a large minimum cut, you can say that almost all cuts have lots of edges. There are very few cuts that have a small boundary. Okay? Actually, I need one lemma I forgot about. So in the expander graph case, we didn't even use the fact that edge errors were independent across edges. Okay, it actually worked even if you just gave an adversary a budget of p times m edges. Here we're going to need to use the fact that the edge errors are independent. How do we use them? We use them in the obvious way. Okay, so just with the Chernoff bound, so remember a bad set is one where half the boundary has been corrupted. You expect only a p fraction of the boundary to be corrupted. So the probability that a full half fraction of the boundary is corrupted is decaying inverse exponential in the boundary size I, the number of edges. Okay, so we're going to use this Chernoff lemma in the grid analysis. Okay? All right, so for a given set with a large boundary, we know it's very unlikely to be bad. It's unlikely to cause us a bunch of errors. So then what you have to do is you just have to show that there aren't too many cuts. Remember, there's an exponential number of cuts in general. You want to show that almost all of them have a really big boundary size, so this Chernoff bound gives you a really good upper bound. Okay? So let me do this slide. This is going to be buggy. Okay? Here's sort of the first thought of how you might do this analysis for graphs. Okay, so we have this Chernoff bound saying the probability that a set is bad is inverse exponential in I. The claim is going to be that the number of connected subgraphs with a given boundary size I is only exponential in I. Okay, so n the number of vertices times 3 to the I. Okay, so the intuition is this is exactly the decay in the probability bound in our Chernoff bound is strong enough to cancel out this kind of growth in the number of cuts with a given boundary size I. Okay? So here's the proposed proof. So we're counting cuts in a planar graph, so we can count cycles in the dual graph. The dual graph to the grid is basically also a grid. So how many cycles can there be in a grid? Well, you pick your first vertex, n choices for that, and it's 4 regular. So you have 3 choices for each of your next I vertices. So that gives you n times 3 to the I cycles over in the dual, and then cuts with a given boundary size I in the original graph. So how do you use this? So now you basically just do a sort of parameterized union bound, parameterized by the number of edges in the boundary, okay? So we're going to be bucketing connected subgraphs according to their boundary size. So in the grid, you can start this sum at 4. That's going to be the smallest boundary size you have to worry about. Remember that the error is just the sum of the sizes of the bad sets. So we're just going to iterate over all of the possible bad sets, all of the connected subgraphs S, and we're just going to look at what would be the error if it was bad and the probability that it's bad. This we know by the Chernoff bound. This is inverse exponential in I. So combining that with the only exponential in I upper bound on the number of cuts with a given boundary size I, that gives us this NP squared as desired. Okay? But this isn't actually correct. You see why? Sample.
Well, the I could be partitioned into several cycles.
Good. Good, exactly. So I'm not actually, so the problem is the lemma. I mean, the lemma is actually just totally false. There's way more connected subgraphs of the grid that have this size boundary, okay? We forgot about, for example, sets that look like this, a donut, okay? So in the dual, right, so what are the cycles that correspond to this donut? Well, it's actually the union of two disjoint cycles. And we didn't count that. We just counted, connected cycles in that argument. Okay? And in fact, there are going to be a lot of these. There's way too many of these for that union bound argument to actually go through. So we need a little trick. So let me tell you about the trick, and then I'll wrap up. So what we're going to do is we're going to generalize the flipping lemma. So the flipping lemma, remember, this is what said that if you're a bad set, then half of the boundary edges have to be bad. So suppose a donut like S is bad. We already know that the union of its two boundaries, at least half of the edges are corrupted. So either the outer boundary or the inner boundary is at least half corrupted. But actually something stronger is true. Both the outer boundary and the inner boundary are more than half corrupted. Okay? So why is the outer boundary half corrupted? Well, previously we were flipping the label of everything in S. Now let's flip the label of everything in S and the whole. Okay? That's again going to toggle the status of everything except of nothing, except for the edges on the outer boundary of S. It'll toggle the status of each of these edges. So if we had an optimal labeling, it must be that at least half of these were thought to be good by the algorithm, and that all of those edges had to have been corrupted in the data. Okay. So that's the generalized flipping lemma, which says the outer boundary has to be half corrupted. And so, if an algorithm incurs errors in a donut shaped like this set S, we just proved that actually the filled-in version of the set is itself a bad set. We were already counting the errors from this filled-in set, and that only overcounts the errors from the donut. So we just charge errors in a non-filled-in set to its filled-in version. Okay? So now what the sum looks like, it's the same sum as before, except when we're summing over the cuts with a given boundary size I, we only sum over the sets that have no holes, okay, that are filled in. Those really do correspond to simple cycles over in the dual, and that's what we upper bounded by n times 3 to the I. Okay, and that gets the calculation to go through. Okay. So let me just wrap up. There's still more open questions. This is not exhaustive. There's just tons of things we don't know. So first, just kind of, most closely related to what I talked about, I showed you a non-example, a path, and 3 positive examples: expanders, graphs with large min cut, and grid-like graphs, all of which have approximate recovery. And I would love to see, some more general understanding of what is the combinatorial structure that permits these approximate recovery results. Ideally, it would be great to have a characterization. Like maybe you could say something like, you can do approximate recovery if and only if you have a weak expansion condition. That would be best case scenario. At the very least, you'd hope to have much more sweeping positive statements than we do that capture a bunch of different graph classes with a common argument. As I said, computational efficiency results, the only one I showed you was for planar graphs, and we really don't know anything outside of planar graphs. Again, it seems like an SDP-based approach would be the first thing to look at based on its success in the stochastic block model. I mentioned a couple times that in the paper it's a more general model where you also get noisy information about the nodes. So I tell you not just information about the parity between two endpoints, but I give you advice that this vertex is a 0, and maybe with 60% probability it really is a 0, but with 40% probability it's actually a 1. Okay, but I give you some, helpful advice about the nodes. Can you use that extra information to get better recovery guarantees? And frankly, in our paper, we weren't able to do much. We sort of used the edge information and then used the node information to break ties. But hopefully, some of you saw Dylan Foster's lightning talk on Monday. There's some nice progress on the model with node signals by Dylan and also Daniel Reichman and Kartik Sridharan. That's just very recent. Okay, so they have some pretty sweeping results when you also have this node information available. And then finally, everything has been just about the binary labeling case. Okay, everything's a 0 or a 1. If you think about image segmentation, sometimes you want to know more than just what's the foreground and what's the background. Sometimes you want to break it into possibly more than 2 regions. That would correspond to a larger alphabet size, okay, bigger than just 0, 1. And we know literally nothing, even for alphabet size 3. The reason being that the flipping lemma already breaks down, or it's not obvious what its analog is once you're beyond the binary case. Okay, so lots to do. Happy to talk more for the rest of the day. Thanks very much. Ken.
So if an edge detector has a problem at 1 pixel, it might well have a problem at the next pixel, which sort of vaguely suggests looking at correlated noise probabilities.
Yep. Agreed. So the comment was rightfully complaining about the assumption of independence. So we can look at these proofs and see what did we really use. For the expanded result, we needed basically nothing. So again, even an adversary who can corrupt an arbitrary p fraction of the edges, the analysis goes through. For the other ones, we needed a Chernoff bound to talk about these bad sets. So if you had a kind of correlation where you could still get Chernoff-like bounds, that should be enough to push everything through. Because all the rest is just about the graph, counting the cuts of different sizes in the graph. Yeah.
More question?
This is related to point 3. If you have true labels, you have access to query for true labels on vertices, but you don't want to query on every label, like vertex. You want to query for very few. Do you have any results?
You're saying like an active learning kind of setup.
So it's like a mixed model.
Yeah, we never thought about that.
It just seems like at least the least you can do to work with larger cluster of graphs, because you can kind of
Potentially, yeah. So the question then, could you get sort of a query complexity which is strictly less than the error rate you get with no queries? Yeah, it's an excellent question. I have no intuition about whether you could beat the error rates or not. So
another sort of different direction. You could imagine multiple edge detection, edge labeling algorithms that not independently, but somewhat dependently, maybe label edges as positive and negative, and each one has an error. Can you benefit from it? Can you use, you had several distorted versions of those ground truths. Does that help you? I mean, is there any way to model this in some fashion?
Yeah, well, you're right. So somehow it's a little bit, so that I would think would, I see. So you're saying, okay, good. So rather than just getting sort of one sample from a distribution, you get sort of multiple samples. Yeah. Good question. We didn't think about that. You'd hope you could do better pretty quickly with multiple samples, but we never thought about it. Yeah.
Okay, so let's take advantage of the break to ask more questions and thank Jimmy.
Thanks.